The first intermolecular force we're going to talk about is the ion-dipole interaction. But first, let me just show you this is what I might call the family tree of intermolecular forces. These are the four that we need to get acquainted with. So ion-dipole is the first one we'll talk about right now. Then comes dipole-dipole, London dispersion forces, and hydrogen bonding. Okay, so I'm sure you've dissolved salt in water at some point, and what's interesting is there's no way you could dissolve salt in water if it weren't for the so-called ion-dipole interaction. So let's take a look at how this works. All right, so here's a kind of a schematic of an ionic compound. We'll say it's sodium chloride for now. So you've got this nice checkerboard pattern of alternating sodium cations and chloride anions, the plus and minus sign. And let's say you drop this into a glass of water. Okay, so now it's it's falling to the bottom of the glass of water. And if we could zoom in and look at what the water molecules are doing to the salt crystal, at the atomic level, here's kind of what things might look like. So here's a water molecule, and now we know that it's water is not a linear molecule. It's bent. It's got that V shape, and furthermore, we know that the electronegativities of oxygen and hydrogen are quite different, right? Oxygen has an electronegativity of 3.5, hydrogen only 2.1. So the oxygen is going to be pulling on those electrons in the two bonds much more strongly than the hydrogens, and as a result, oxygen is going to have a significant partial negative charge, and the two hydrogens are going to have a little bit of positive charge. So this is what we call a polar molecule. It's it's quite polar for its size. Now, when these little guys are kind of swimming around and interacting with the salt crystal, there's a preference. The water molecule, when it encounters, say, a negatively charged ion, it's not going to orient itself in any random way. It's going to want to present the positive charged hydrogens closest to the negative charges, because opposites attract. We see this over and over in chemistry. So this is these are just a couple of examples of water molecules and how they might orient themselves around the salt crystal. And then on the other hand, when the water molecules are interacting with the positively charged ions, it's going to want to point its oxygen at those guys, so that you again get an opposite charge interaction, which is very stabilizing. So little by little, the water molecules will pick off the ions, and basically they like vultures on a carcass. It's going to pull the ions off of the crystal and pull them into the water. And so then if we could see the sodium and chloride ions sort of suspended in the water molecules would look like this as they surround each one. And it's a very ordered system in a way, because again, the waters, they want to point the hydrogens at the negatively charged ions. They want to point their negative charges, the oxygens, at the positively charged ions. And then here I'm overlaying the dipoles on the water molecules, just so that you can see how it's a very directional kind of ordered system. Okay, so that's so let's just back up a little bit and summarize. So we can say that polar solvents like water are usually good at dissolving ionic compounds. The dipoles on these polar molecules strongly attract ions of opposite charge. Okay, so that's basically, if you kind of follow that, that's ion-dipole interactions in a nutshell. Now, let's see if we can walk through an actual example and see if we can apply what you just heard. So here's an exercise that I'd like you to try to do. So please push the pause button and see if you can create an illustration. Okay, so hopefully you've started to kind of get your mind around the problem, and let me see if I can get my pen working here. All right, so it says we've got lithium chloride, which is clearly that's an ionic compound, and we're going to dissolve that with, let's say we have liquid ammonia. All right, so how would the molecules of ammonia orient themselves around the lithium and the chloride ions in solution? Okay, so first let me just draw, we know that lithium, when it ionizes, forms the plus cation, chloride the minus. So I'm just going to start by drawing a circle with a plus sign in the middle to symbolize a lithium cation, and over here I'll just draw a big circle with a minus sign, and this is going to symbolize chlorine. All right. Now, let's say, let me see if I can change my pen color here. I wonder if I can do this. Okay, so ammonia, so we have to draw the structure. So first of all, that ammonia, NH3, the Lewis structure is going to look, like this, right? It's got 5 valence electrons. And we know from our work in molecular geometry that the three-dimensional shape of ammonia is trigonal pyramidal, right? So it's going to be like a little tripod, a little pyramid. And first, let's just do a reality check. So if we want to illustrate an ion-dipole interaction, the lithium chloride, they're bringing the ions. Hopefully ammonia is going to bring the dipole to the party, right? Because we can't have an ion-dipole interaction without a dipole. Does ammonia have a dipole? Well, sure it does, because if you look at the electronegativities of hydrogen and nitrogen, nitrogen 3.0, hydrogen 2.1. So if you draw each of the 3 bond dipoles, they all point toward the nitrogen. And as a result, these do reinforce each other. They're not in the same plane. It's not a trigonal planar molecule. This is like a little pyramid. So the total net dipole is going to be pointing right straight up through the nitrogen. So, oh yeah, we'll definitely have a dipole. And when the ammonia molecules surround the cation, are they going to want to point their hydrogens at the cation or the nitrogen? Okay, so hopefully you're thinking, nitrogen, because that's the negative. That's the negative end. So, I won't go on and draw all of them, but you need to orient the nitrogens to show that the negatively charged nitrogen is pointing at the cation. Okay, and I would, for a complete drawing, you might draw at least one more, just showing, maybe draw another one kind of like this. Okay, and obviously I ain't Picasso here, so just do your best, but make it clear that nitrogen is pointing at the cation. Now, conversely, it's the hydrogens that are going to want to interact with the anion, right? Because if the hydrogens are slightly positively charged, then of course they're going to want to interact with the negatively charged ion. Okay, so again, you'd want to maybe draw another one up here showing the hydrogens interacting with this guy, and then you're good. Then you got it. So this is what I mean if I say draw a diagram illustrating the ion-dipole interaction. This is kind of what I'm looking for. I just want to make sure that you understand how the molecular dipole is oriented and how it's going to interact with the positive and negatively charged ions. Okay, and then I'm not going to go through this one, but why don't you try one more? Why don't you try doing this one? Calcium chloride dissolved in, this would be called methyl chloride. All right, but from the molecular formula, you're going to know how to generate the 3D structure and then get the dipole. Okay, now here's another example. Let's say instead of having a polar molecule, let's say we have a different molecule that's really not that polar. So here's an example. I've drawn two Lewis structures that each represent molecules of heptane. Heptane is an organic solvent. It's a hydrocarbon. The molecular formula C7H16. And, this is the reason this is not a very polar molecule is, if you look at the bond polarity here, carbon has an electronegativity of 2.5, hydrogen 2.1, so the difference is only 0.4. And then along the backbone, you've got all these carbon-carbon bonds, so there's no electronegativity difference in there. So overall, it's a very weakly polar, and it's not really considered a polar molecule at all in chemistry. So if you drop a crystal of sodium chloride in a beaker of heptane, really there's not going to be much, not much is going to happen. And, as the heptanes approach the sodium chloride, there's not going to be much attraction at all. And I think what you'll find, and we actually saw this in lab, didn't we? Trying to dissolve sodium chloride in heptane is pretty boring because the sodium chloride just kind of sits there and looks at you. So now, we're just about done here. So I think we can summarize by saying that nonpolar solvents, like heptane, they're not very good at dissolving ionic compounds. And that's because nonpolar molecules, they lack dipoles. And the electrostatic attraction between these kinds of molecules and the ionic compound is just not strong enough to draw the ions into solution. So I will leave you with a couple of questions, and this is it for this video. As you know, molecular iodine is a dark purple solid compound. Do you think iodine is going to dissolve easily in water? And what about heptane? Okay, thanks, and I'll see you at the next one.